An important relationship in electrochemistry is the Nernst equation. The Nernst equation relates the concentration of our reactants to the cell potential and allows us to make important predictions about the spontaneity of electrochemical reactions. So the cell potential, which if it's the standard cell potential we indicate as E0 cell, is also referred to as the electromotive force. So our book doesn't do this, but you'll see this frequently referred to in this way. The electromotive force is, in a general sense, can be thought of as being the force with which electrons are being pumped or pushed from the anode to the cathode. What I'm really getting at here is that the cell potential is a measure of the spontaneity of the cell, and it should be related to delta G, and it should be related to K. And what we know about the cell potential, or the EMF, is that the cell potential must be greater than 0 for a spontaneous process. So, delta G naught, K, and cell potential are all measures of the spontaneity of a process, and it should be possible to relate all three quantities. We know that a process will be spontaneous if delta G naught is less than 0, or alternatively, if the cell potential is greater than 0. We also know that if Q is less than K, then our reaction will spontaneously move to products. We also know that when K is very big, then we have a very favorable process. So previously we have defined delta G as the amount of energy available to do useful work. So when we're talking about a voltaic cell in which electrons spontaneously move through an external circuit from an anode to a cathode, the electrical work that's done, we can just label that as W electric, and that's equal to the change in Gibbs free energy of our cell. Now the change in Gibbs free energy of our cell will be less than 0 for a spontaneous process. So what is this work that is done? Well, the work that is done on the surroundings by a voltaic cell is given by the following relationship, where we have minus C multiplied by the cell potential gives us the work done. And what C is the charge that is transferred or moved through the external circuit, and in this case that's going to be electrons moving from the anode to the cathode. So how much charge is transferred? Well, the charge that's transferred is going to be directly related to the number of electrons transferred. The more electrons we transfer, the greater the amount of charge that we will be transferring. So one electron has an electrical charge of 1.6 by 10 to the minus 19 coulombs. And a mole of electrons just has this number multiplied by Avogadro's number. So that's going to have the charge of 1.6 by 10 to the minus 19 times by Avogadro's number. So a mole of electrons has a electrical charge of 9.65 by 10 to the 4 coulombs per mole. So 96,500. Sometimes you'll see this more precisely written as 96,485. Just use the value that's appropriate for the context that you're working in. Okay, so the charge on a mole of electrons is called Faraday's constant and is given the symbol uppercase F in honor of Michael Faraday, who did much of the foundational work on the study of electricity. So the total charge that's going to be transferred in a redox reaction is just going to be equal to the number of moles of electrons transferred multiplied by the charge of a mole of electrons, which is Faraday's constant. So this number n here just represents the number of moles of electrons transferred, and it's important that you become effective at determining this number of moles of electrons. So the work done by an electrochemical cell is equal to the negative of the charge transferred multiplied by the cell potential, and the charge that is transferred is equal to NF, so we can write that the electrical work done is equal to minus NFE of the cell. Now, keeping in mind that the electrical work that is done is exactly the same as a delta G, then the important relationship here is that delta G cell is equal to minus NFE cell. So if we're at standard conditions, then this would be delta G naught of our cell is equal to minus NFE naught of our cell. Now, this is just kind of by the way, Gibbs free energies have values of, they're in energies, so they're in joules. But if we do the dimensional analysis on the other half of our equation, we'll see that we end up with some different units. We end up with units of coulombs volts. So N is our moles, F is Faraday's constant, which is coulombs per mole of electron, and then our cell potential has units of volts, so moles cancels out, and we end up with units of coulombs volts. So 1 joule is exactly the same as 1 coulomb volt, so don't be put off by the fact that your dimensional analysis might look a little unintuitive when you're solving these problems. So a typical problem might be calculating the standard Gibbs free energy for a particular cell. So in this case, we're going to look at our cell that's kind of familiar to us. It's a cell where we've got a zinc 2 plus zinc anode and a copper 2 plus copper cathode. And so the zinc solid gets oxidized to zinc 2 plus, and the copper 2 plus gets reduced to copper. So if we want to calculate the standard cell potential for this guy, we're going to do the standard reduction potential of our cathode, which is our copper 2 plus copper pair, minus the standard reduction potential of our anode, which is the zinc 2 plus zinc pair. And then when we do that, we get a standard cell potential of 1.104 volts. So how many electrons are being transferred here? Well, we can look at this by looking at, we can figure this out by looking at oxidation numbers. So we've got 0 there, plus 2 there, we've got plus 2 there, and 0 there. So hopefully what we see is that 2 electrons are being transferred, because every time we change an atom's oxidation number by 1, that means that we are transferring 1 electron. So N in this case is going to be 2, F is Faraday's constant, E naught cell we calculated using standard reduction potentials. So there we are, we get a Gibbs free energy of minus 2.13 by 10 to the 5 joules. Or if we want to turn that into kilojoules, that's minus 213 kilojoules. So it's a negative, which is good because E naught cell was positive, so that means it's spontaneous. Therefore, we would want delta G naught to be negative in order to be consistent with this being a spontaneous process. Okay, so here's another one. It says, what is delta G naught for the cell based upon the following 2 electrodes? So these are both written as standard reduction reactions. So what we're going to have to do is to find the one that will be the cathode. We're looking for the most positive standard reduction potential, because that is the one that will go in the reduction direction. So we can see that it's going to be our mercury 2 reduction that will be our cathode, and then our zinc reaction that's happening at the anode will actually be the reverse of this. What our anode is going to be is zinc going to zinc 2 plus 2 electrons, because it has a smaller value for its standard reduction potential. So let's calculate the cell potential here. It's always cathode standard reduction potential minus anode standard reduction potential. So 0.851 minus negative 0.7618. So that gives a standard cell potential of 1.613 volts. So E naught cell, this is a spontaneous process. It's greater than 0. So I know that delta G must be negative. How many electrons are being transferred? Well, it's going to be 2 electrons, isn't it? So this is my anode reaction. And then my cathode reaction will be that guy. So what's really happening is 2 electrons are being moved from solid zinc to the aqueous Hg2+. So my N here will be equal to 2. So minus 2 times Faraday's constant, 9.65 by 10 to the 4 coulombs per mole, times by the standard cell potential, 1.613 volts, and then that's going to give me minus 3.11 by 10 to the 5 joules, or if I want, I can express that in kilojoules, and I'm happy because it's a negative number. One of the tricky things can be to figure out this number of electrons transferred, but if we do have the overall balanced redox equation, it's not too hard to do this using oxidation numbers. The key thing is to pay attention to the changes in oxidation numbers and also the number of atoms that are involved. So if I look at this balanced reaction here, I've got 2 nickel atoms there. Here we go. 2 nickel atoms here. They both start off with a 0 oxidation number and they change to +2. So the change in oxidation number is just equal to the number of electrons that is transferred. But the only thing is we have to just keep into account the number of atoms that are involved. So every nickel atom here is being oxidized by 2 electrons. But there are 2 nickel atoms. So what that really means is that there are 4 electrons being transferred here. Because this is an oxidation, it is 4 electrons that are being lost. Now, if I look at the oxygen atoms here, I see that oxygen is present in the reactants in 2 forms, as O2 and as water. There's only one form for oxygen in the products. So in the reactants, those oxygen atoms that are in the elemental form have oxidation number of 0. Those that are present in water have oxidation number of -2. So in the products, we have a total of 4 oxygen atoms, but they're all present in the -2 oxidation state. So the oxygen atoms that are present in the water are neither oxidized nor reduced. Their oxidation number does not change. But these 2 guys over here, so we can say that there are 2 of them, they are reduced by 2 electrons. So that means that 4 electrons was gained by those oxygen atoms. So what's happened, how many electrons were transferred? 4 electrons were lost by the nickel, and then 4 electrons were gained by these oxygen atoms here. So in total, we had 4 electrons being transferred. So the take-home message here is that by examining the balanced redox equation, if it isn't clear how many electrons are being transferred, we can figure that out using oxidation numbers. We have to take into account 2 things. We have to take into account the change in oxidation number, but we also have to consider the coefficients and how many atoms are involved as well. Okay, so let's go back and have a look at our, our old friend, the zinc copper voltaic cell. And we know that if we hook this cell up, that zinc will be oxidized. That's what's going to happen at the anode. And copper 2+ ions will be reduced at the cathode. We can calculate using standard electrode reduction potentials that the E0 cell for this setup would be about 1.1 volts. So an interesting question to ask is, when will electrons cease to flow in that cell? And the simple answer is when the limiting reactant is consumed. So we know that our zinc anode is getting consumed. So we could imagine that if we ate away all of this electrode, so it was no longer sitting in the electrolyte, then electrons would cease to flow. This piece of metal would be out here. It would just, wouldn't be able to function anymore. We would have consumed all of our anode. The other thing that might happen is that we could consume all of the copper ions, which are plating out onto our cathode here. And if the concentration of those guys drops to 0, then there's nothing left to be reduced. And as a result, E cell would drop to 0. So when do electrons cease to flow? When we've consumed all of the limiting reactant. So eventually what's going to happen is the cell potential will drop to 0, right? So this cell potential is not fixed. It's going to vary as the reaction progresses. Now previously we had said that the Gibbs free energy change for a reaction will change depending upon what the value of Q is. In particular, the Gibbs free energy change for a reaction under non-standard conditions is equal to the standard Gibbs free energy change plus RT log Q. Now we had previously developed this relationship here relating the cell potential and the Gibbs free energy change for a reaction. And of course, if this was the standard cell potential, that would be related to the standard Gibbs free energy change for our reaction. So what I'm going to do is I'm going to substitute these expressions into our reaction that tells us about the Gibbs free energy change under non-standard conditions and develop a new equation which is referred to as the Nernst equation. So what the Nernst equation does is it gives you the cell potential after the cell has been running for a little while, basically under non-standard conditions. So it says that the cell potential will be equal to the standard cell potential minus RT on NF log Q, where Q, if you remember, is what we call the reaction quotient. So that's how this works, right? So it's a modestly complex formula here. All right, so what does the Nernst equation predict? Well, what's going to happen as our cell runs, right? What's going to happen as our cell runs is reactants, they're going to decrease, and products, they're going to increase, right? Now, Q, of course, is computed by taking our product concentrations and dividing them by our reactant concentrations. So our reactant concentrations are going to decrease, our product concentration is going to decrease, so as time progresses, we're going to be expecting that Q will get bigger and bigger. So what's going to happen? We're going to start, as Q gets bigger and bigger, we're going to be subtracting away from our cell potential a bigger and bigger and bigger term. And eventually, this is going to drop to 0 once all of our reactants are consumed. So what's going to happen as time passes? Our cell potential is going to drop. So let's have a look at this. It says the standard potential of the voltaic cell based on the zinc copper 2+ ion reaction, and then it gives the reaction here, we know this, is 1.104 volts. What is the value of the cell potential at 25 degrees Celsius, or 298.15 K, when the copper 2+ ion concentration is 0.1 mole per liter and the zinc ion concentration is 1.9 mole per liter? So this is really describing a cell where we started at standard conditions and we consumed 90% of our reactants. So this is what I'm saying here. What happened is we started initially with that being at 1 molar and that being at 1 molar. So that's standard conditions. And then this went down by 0.9 molar and this went up by 0.9 molar. And so under the conditions that we're interested in, this is at 0.1 molar and this is at 0.9 molar. So we've consumed 90% of our reactants. So what are we expecting the cell potential to be? Well, we're expecting the cell potential to be less than the standard cell potential. Okay, so let's see how much less. So E cell is going to be equal to the standard cell potential minus RT on NF. And in this case, it's 2 electrons that are being transferred, so N will be 2. multiplied by log of the reaction quotient. Remember that solids don't appear in the expression for the reaction quotient, so this will just be our product ion concentration, our zinc 2+ ion concentration, divided by our reactant ion concentration, copper 2+. There we go. So that's our Q. So 1.104, our standard cell potential, minus R, 8.314, multiplied by T, 298, divided by NF. N is 2, F is Faraday's constant, 9.65 by 10 to the 4, multiplied by log of our reaction quotient, log of 1.9 being our, so that should be 1.9 there, 1.9 being the log of our, being the concentration of our zinc 2+ ions, and then 0.1 being the concentration of our copper 2+ ions. And I put all of that into the calculator, and sure enough, my cell potential, when I've used 90% of my reactants up, is significantly lower than my standard cell potential. Now, it's a little lower, but it's not like that much lower, right? And the reason why it's not that much lower is because there's a logarithmic dependence on the of the cell potential on the reaction quotient. So it tends to not decrease that quickly, but then it sort of tends to go off a cliff. So it kind of tends to decrease sort of like that. Okay, so here's a little diagram showing this here. This is for a lead acid battery, the type of battery that you have in your car. You can see why it's called a lead acid battery, because two of the key components here are lead and acid. And one of these cells has a standard cell potential of just about 2 volts. They put 6 of these in series and you get a 12-volt battery. And what you can see is that it decreases pretty modestly until you're like, over 90% discharged, and then it just kind of drops off. It goes off a cliff. And you might have experienced that where you've been trying to start your car, and it's all going well, and then all of a sudden you have like no battery very quickly. So that's because in the Nernst equation, there's a logarithmic dependence of the cell potential on Q. Okay, so when the cell reaches chemical equilibrium, delta G equals 0, the cell potential equals 0, and Q equals K. So we can put those values into the Nernst equation and get a relationship that relates the standard cell potential to the equilibrium constant. So when we are at equilibrium, E naught cell, 0. Q is equal to K. Okay, so that's what we've got here. So 0 and then K, and then now we're going to kind of reorganize, and we can see that the standard cell potential is equal to RT on NF log K. So all I need to do to figure out K for an electrochemical reaction is turn it into a cell. I have to put a salt bridge in, of course. Have a voltmeter in here. If I measure the cell potential, then I can just plug it into this little formula here and I get K. So it's a really convenient way of getting a K for a redox reaction. Okay, so here's a super complicated reaction. It's the oxidation of copper by nitric acid, and it makes this nice brown gas called NO, nitrogen monoxide. So what do we got here? We got 3 coppers reacting with 8 H pluses and 2 nitrate anions to give 2 NOs, and 3 copper 2+ ions and 4 moles of water. So the first thing we're going to do is determine the standard cell potential for this reaction. We know how to do that, don't we? It's cathode standard reduction potential minus the anode standard reduction potential. So breaking this into 2 half equations, we have the reduction of the copper, and that has a standard reduction potential of 0.3419 volts. And then our cathode reduction is this reduction of the of the nitrate anion to give NO, and that has a standard reduction potential of 0.96 volts. So to get the cell potential, cathode minus anode, we don't have to reverse the direction of anything, remember that, or flip the signs or anything like that. It's just straight up standard reduction potential of the cathode minus the standard reduction potential of the anode. So 0.96 minus 0.3419 gives me an E naught of 0.6181. So that's the standard reduction potential. What we're going to do now is we're going to calculate the cell potential when the concentrations of things are nowhere near standard conditions. So standard conditions, everything would have a concentration of 1 mole per liter. But what we've got here is we're still at 298 K, but the concentration of H plus is 0.1 mole per liter. The concentration of nitrate is 0.025 moles per liter. The concentration of copper 2 plus is 0.0375 moles per liter. And the concentration of NO is 6.13 by 10 to the minus 5 moles per liter. So my guess is, because this is so low, it's probably really going to be very, very favorable. It's probably going to be more favorable than if everything was at 1 mole per liter, because that's really, really low. It's probably going to rush to kind of try and make some of that stuff. So my guess is that under these conditions, that the cell potential is probably going to be a bit bigger than the standard cell potential when everything had completely equal concentrations and it was 1 mole per liter concentration for everything. So let's do the math. It's going to be a bit of a beast because Q is going to be complex for this because we've got a lot of weird coefficients. The thing to remember though is that we don't need to include any solids or pure liquids in our expression for Q. Okay, so let's go ahead and calculate it. Remember that the cell potential under non-standard conditions is going to be equal to the standard cell potential minus RT on NF log Q. And so let's go ahead and do that. N is going to be a little bit of a beast to figure out. You only have to look at one atom here. So that guy's 0, that guy's plus 2. So 2 electrons were transferred for 3 copper atoms. That means 6 electrons were transferred. So there's my N. This is Faraday's constant, R, my temperature, and then I've got to do log Q. So it is the copper ion concentration has to be cubed, there it is. The NO concentration has to be squared, divided by the hydrogen ion concentration has to be raised to the power of 8, and then the nitrate ion concentration needs to be squared. And I do all of that, and I got a number that was a tiny little bit bigger than the standard cell potential, which I'm kind of like feeling that that's like what I intuitively would expect, because we had a very low concentration of the NO and these fairly high concentrations of all of our reactants. So that's going to be pushing that equilibrium to the right hand side according to Le Chatelier's principle. Okay.